everyone, or good afternoon, or good evening, whenever you may be viewing this. This is one a day 13 Gaussian quadratures for Math 345 numerical analysis. So we're going to introduce this video, and then, or in this video, we'll introduce the idea of Gaussian quadrature and how it's used. Maybe go over some technology and demonstrate its purpose, and then leave the rest in the notes for you to explore. All right, so Gaussian quadrature comes about because everything up to this point, all of our estimation properties have really depended upon the use of polynomials and with equally spaced nodes to get a good handle on the approximation. And there's a lot of positives with this, but there are some downsides. In particular, the even spaceness of the nodes may create situations where, for example, wasn't intending to do this, but I'll just throw this in here. So let's say our function does, it's kind of cruising along, and then it has maybe something like this, and then it's kind of cruising along again. So if our nodes are equally spaced and we miss this rapid deceleration in this section, okay, we may get a very gross error introduced here, or we may miss this whole value incompletely. And so also, another thing to note is that the relative change in kind of like this region and also in this region are essentially the same. So we're losing a lot of computational power in spending time computing values of these nodes. Since there's not much change happening here, we can get away with larger spaced intervals to accompany the area under the curve here and here. So the identification or the invention of something like this Gaussian quadrature, what it's doing is it's trying to compensate for more efficient use of computational time by reducing the number of nodes that we need and therefore reducing the number of calculations, which also reduces the number of opportunities for error to be introduced. That's one really big positive. And the second thing is that if our nodes aren't, if the evenness of our nodes, the spacing between our nodes is in a direction where we miss, sections of our curve that have this rapid change, this rapid deceleration, for example, we're going to get again more error, but also we're going to miss the value of the function itself. And so the purpose of Gaussian quadratures is to really provide feedback, if you will, on when is it appropriate to make larger guesses for our nodes in between our distances here. In other words, can I put a node here, maybe here and here, instead of doing a node, every so like that. So instead of having evenly spaced nodes in this region, can I do something like this where I'm spacing them out because the change in the function is not so much, and then maybe our nodes here were good, or even low space nodes would capture this relatively quick descent, or maybe we need to make a bunch of nodes here to capture if it's a really steep descent. For example, like 1 over x near x equals 0. You may want to significantly increase the number of nodes there to indicate or to measure the rate of change there. And then over here again, if we're doing these evenly spaced nodes, we're going to have a bunch of data points that really could we interpolate this with a few data points, right? So the distance is what I'm referring to in terms of in between the nodes here. So that's the two big areas of concern with respect to the Gaussian quadratures that you really have a benefit for this method. And so let's kind of explore that a little bit. So the Gaussian quadrature chooses 4 points for evaluation. Should learn how to speak English more better. So when you're writing stuff down, you're in your head, you're not really thinking about what it sounds like. I guess I should have read this anyways. Evaluations for an optimal rather than an evenly spaced way. So that's exactly what I'm referring to here. Okay, so this is kind of like the picture to think about for those words. So the only requirement though is that our nodes are x1 through xn, that they're inside the interval, right? The area, they're in the region that we're interpolating. So we have those nodes, those n nodes, and then we have the coefficients for some polynomial, C1 through Cn. And so if we can choose those to minimize the expected error with the approximation of f of x, the integral from a to b of f of x dx, as the sum of those coefficients and the sum of the functions evaluated at those values. What that's creating is really an opportunity for two n parameters, n of them coming from the number of nodes being evaluated, and then an n also for the number of coefficients that correspond to each of those function of evaluations. Okay, so we have these two parameters that we're really trying to maximize, and that produces a polynomial of n 2n minus 1 degree. Okay, in other words, it's always one less than the degree of the number of nodes that you have. A simple example is if you have a node, you have a zero order polynomial, and if you have two nodes, right, what you can draw through that is a line, so that would be a linear. So it's always 1 degree less than the total number of nodes or nodes that you have. Okay, and so in that then, suppose, just an example to kind of get our grounding and make sense of this. Suppose we have, let's say, two unknowns, right? Two coefficients and two data points, right? Two nodes. Okay, and we want to approximate the integral from -1 to 1 of f of x dx. Okay, well, that's approximately equal to the first coefficient times the evaluation of the function at the first node plus the second coefficient times the evaluation of the polynomial or the function at the second node. Okay, so that's going to give us then, we have 2 times 2 minus 1. So we're going to get a third degree polynomial out of this, which means for us, we're going to have f of x is equal to a naught plus a1x plus a2x squared plus a3x cubed. Okay, so you can see we have 1, 2, 3, 4 unknowns there that we're trying to gather some sense around. Okay, and so there's no rhyme or reason why we couldn't say that finding the exact values of the function at f of x equals 1, x squared, and x cubed means that we need to find the values of c1, c2, and x1 and x2. Okay, and so in order to do that, let's go ahead and create the system. So c1 evaluated at f of 1, and c2 evaluated at f of some x, and that gives us 1. I guess there should be more. That may be confusing, so let me clarify. We're saying that the value of f of x is equal to, we don't know what the x value that produces that is. We're saying the value of the function f is 1 at these points, and then we're going to integrate that over the interval, which gives us from -1 to 1 of 1, gives us 2. And so we're going to continue that thing for the same idea for let's see, we have here x, x2, x squared, and x cubed. Okay, so that's going to create then these systems of equations. And so so it's going to give us the four unknowns with four equations, which creates an augmented matrix, which is simple to plug into. I plugged it into GeoGebra, for example, and get the coefficients out. And so what we find is that the coefficient for C1 is 1, C2 is 1, x1 is the cube or the square root of 3 over 3, and x squared is the cube root. No, sorry, the square root of 3 divided by 3. Okay, so these are the values then that provide us for it, and it becomes apparent then that the solutions to these values are the solutions to the Legendre polynomials on the interval from -1 to 1. And the Legendre polynomials are shown here. So P0 of x is equal to 1, P1 of x is equal to x, P2 is equal to x squared minus 1/3, and P3 is equal to x cubed minus 3/5 x, and so on and so forth. So you can generate as many of these as you need. And Legendre polynomials have a lot of great properties. We'll use more of these much later in the semester, actually, as a basis set for some additional work that we'll be doing there. So that's exciting to explore. So that's kind of the idea then, that we create these values that allow us then to approximate this integral, and it gives us a really nice relationship to corresponding reduce the number of calculations for our estimation or numerical value. That brings us then to this idea of this key theorem, which states that suppose we have the nodes x1 through xn, and these nodes are roots of the nth order Legendre polynomial Pn of x for each I from 1 to n. Then these numbers, these c to the i's, are defined by, and such that the c to the i's, I should say a little bit more explicitly, are defined by this relationship that they're equal to the integral from -1 to 1 over the product, where j is not equal to I of x minus x of j divided by xj minus x of uh, dx. So if we, that's a j. So if we integrate each of those polynomials, those coefficients over this value, those integrals then will be the roots that we need. These will be the coefficients then that will define the value. And so then our estimation then for p of x, as long as it's less than degree 2, for the integral from -1 to 1 of our function we're trying to estimate, is just going to be equal to the sum, this estimation from 1 to n of the coefficients that were defined here times the polynomial, this p of x, evaluated at the Legendre uh, zero roots. Okay, and so that's really helpful. That gives us a really good estimation, and so it reduces the number of calculations that we have or that we need in order to get a really good approximation for this function. And then the last thing I just wanted to tackle is that you may notice that these limits of integration are always between -1 and 1. And so you can actually, if you have an integral, let's say between, I don't know, let's say a and b of f of x dx, you can actually translate that into an integral over the region from -1 to 1 if you let t equal 2x minus a minus b over b minus a. So if you make this substitution, then you plug that in, and with a change of limits as appropriately stated, this will be the change of limits will result in a result from -1 to 1 over that region, and then you're going to have the function evaluation of f will be from b minus a times t plus b plus a, all divided by 2. And then out here, you're going to have a b minus a divided by 2. That's going to result as a product times dt. And so these two relationships correspond. And so that's how you would map a function if you're trying to approximate a function over a region that was not equal to -1 to 1. This substitution will allow you to translate it into a function of this form, and then you would use this theorem to approximate that value. So I just wanted to kind of throw that in as a bow to tie up that piece. And then the last thing I'd like to demonstrate is if I can jump over to from our handwritten stuff here to some technology. I'm going to pause this and calculate the zeros, the CIs. You can do that by looking them up at a table, for example. You should note that there's a lot of symmetry with the roots due to the polynomial, those genre polynomials. I created this in GeoGebra, so I just made a slider. Mine goes from 0 to 9 because I don't imagine going beyond that. And if I go to 10, at least mine tends to shut down. So if I need more than that, I'll probably have to either Google it or allow the computer to compute that time. So I define the function Pn of x. And so this is the Rodriguez formula as the recurrence relationship that generates them. It creates a list of the zeros, which you'll see here as list 1. And then I pulled out those exact values in list 2 here. And so when I move my slider here, you can see how it's changing the polynomial. So this is the degree 1 here. I can't get the n here yet to match the degree, but you can see what the n is here. So this is the constant value, so there is no zeros there. The linear one goes through 0, so that's p of x equals x. In 2, we start to get, and that's what we just saw for, right? In the example coming up, we're looking at these values of p and the x. So you can actually see how they're being computed here. I had to set up the rounding to 10 decimals just to try to get as much accuracy as I could. And so here I'm getting 3 nodes, and then going a little further, there's 4, and so on and so forth. So you can see as this Legendre polynomial is dancing between the zeros, you're getting the values here, and these would be then the CIs that you're using to evaluate your function. Okay, so I just wanted to show you this technology component and how it's creating the zeros. And so let's look at an example of this Gaussian quadrature. So Let's say that we want to find out the value of the Gaussian from 1 to 1.5. So we're going to find the area under the curve of e to the negative x squared dx. Okay, and so notice that our a and b are not from -1 to 1. So utilizing the substitution, connecting the change in variables to t is equal to this 2x minus a minus b over b minus a. Using this substitution produces then this relationship here, and also then a relationship for the dx. So this part right here is the substitution of dx, and we're replacing here, solving this for x, is what allows us then to write this for over the interval from -1 to 1. Okay, so we're going to do that, and then that will allow us then to approximate the integral, knowing, uh, as we showed earlier, the connection with, sorry about that, I had a little frog in my throat, showing earlier than the connection to the Legendre polynomial as the optimization for the nodes, and computing the coefficients that correspond to each of those cases. So in the first instance, we're going to have n equals 2 as our approximation there. And so we'll utilize technology to find the roots. But what we're trying to find here is the roots of, I guess I should put all in the same line, huh? So n equals 2. So the roots of the CI. So we're going to have two roots for the polynomial, for the Legendre polynomial P2. So P2 of x equal to 0. So we're going to solve that. And then also we want the CI for those two close together. So the roots and then CI. So the CI, remember, come from the relationship that we're going to integrate from -1 to 1. J equals 1 to n, where j is not equal to I of x minus xj over xi minus xj, and then dx. So we're going to integrate those results or those values, and find those values then to correspond to the value. And so then that the integral from -1 to 1 of f of x dx. So just kind of setting up or writing out what I'm going to try to say. I'm setting up what we're writing, or writing out what we're setting up in the technology, so that way it won't seem so out of the blue, and you can kind of see the connections to each of the different components here. So here f of x is equal to, again, this relationship, plugging that in. And so we want to plug in the values of this. And so we're going to have 1/4. Where's that coming from, you might ask? Well, up here we have 1/2, 1 and 1/2, or 3/2 minus 1 divided by 2. So that's 1/2 of 1/2, which is 1/4. So that's where that's coming from. And then we're going to be multiplying that whole thing, because that comes out of, this constant comes out of the entire integral. We're going to be multiplying that by the corresponding C1, right? And so it turns out for n equals 2, that's going to be 1. So this is C1, and then the corresponding E, well, that's going to be F of all of this fun here, but evaluated at the value of the root of this value here. So this value is going to go in there, plus, and then this is going to be my C2, which is going to also be 1. That comes from here, and we'll show that in the derivation in just a second. And then F of, and so again, this value is here, and we're going to take the root that we got from P2, second degree polynomial, and evaluate it there. And so then the combination, this linear combination of this product of the CI with the F of Ri, I guess, the root, right? Evaluated at each of those. This approximation will be the case for when n is equal to 2. And then it'll look very similar for n equals 3. N equals 3, we're going to have the roots, and this time we're going to have, I guess I can say, like, I don't want to call them this one, R1, R2, and R3. And then we have our CI, so we'll have C1, C2, and C3. That looks better. That's a little bit nicer. Okay, so you're going to have 1/4, then times C1. Uh, that's the C1 here. It'll be different for n equals 3, and then times f of R1 plus C2 f of R2 plus C3 f of R3. Okay, so that's what we're establishing. That's what we're setting up. So we're going to use technology to do the actual computations of each of these components. But I just wanted to kind of provide a what looked like a really badly drawn football play of this Gaussian approximation for this example. Okay. All right. So let's jump over to the technology and put this action into work. All right, so here's the technology. So to set it up, we first created the slider, and then we put in the Rodriguez relationship, which is what you see here, which generates the Legendre polynomials. And then we needed to find the roots. So here is the roots. This is how we're going to find the roots. Now, granted, for n equals 0, we have a constant function for the Legendre polynomial. That's just equal to 1. It's up there. You can see it here. So it doesn't have any roots. That's why I have the question marks here. Okay, and then this creates a set of ordered pairs. And so I just want the x components of that. And so that's what this list 2 is creating. The x of L1s is taking the x component of the ordered pairs generated from the roots. Okay, here I have them as sliders, but I just set, this is my a and my b from the original integral for f of x from 1 to 1.5. And then I have a relationship that I'm using to compute the coefficients instead of doing the integrals and the products, a relationship between this. And so I first need the derivative of the polynomial, p to the n, and then I can generate the sequence of coefficients using this relationship, 2 divided by 1 minus the x component of the root squared times the derivative evaluated at that root squared. And so that then gives me the opportunity to compute each of the CIs. Okay, and then here's my h of x, which is really the f of x in the original problem. So here I'm inputting in the values to transform it so I can integrate from -1 to 1. This is the change in variable, if you will. And so I have this times the dx term. So I plugged in everything here. So that's what I'm evaluating. And then here I'm actually computing the integral by summing over the products of the list 3, which is what's generated from the coefficients times the function evaluated at this change of variables. So it's this thing. And so as we go through, you'll see for n equals 2, well, first of all, there's no estimate when there's no area, right? And then our first, for n equals 1, we get 0.104, and that's actually pretty accurate because the actual value is like 0.109, and so this is accurate to 2 decimal places already with just a linear approximation, so that's pretty good. If we go to 2, n equals 2 here, you see that we get the value of 0.10940, and if I cut it off at the number of digits of significance for this example, this value would be 3. I'm going out to 10 digits just to reduce the amount of error. Okay, and then if I go to n equals 3 here, you'll see that I get even more accuracy to the actual value. And in fact, we could actually compare the absolute value or the exact value for this and see what that value is. Let's go ahead and do that real quick. So let me move over here. Great view. I hadn't planned on doing this, but it makes sense to incorporate that. So I was trying to substitute something there. Okay, so let's do integral. How about if we do in integral? In integral. And so we're going to do a exponential negative x squared. And we're going to go from x equals 1 to, actually I could probably do a to b since those are defined. And so you get, there's the exact value. Let me copy that value and plug that in here. Okay, so there's the exact value. So that's going to be d. So the absolute value of d minus c, this will give us the absolute error. And so you can see it's good out to that many decimal places. And so if I go d for n equals 2, you can see it's good out to the 1, 2, 3, 4. So 10 to the minus 5. And for n equals 3, it jumps over 2 places. So it is significantly accurate just with n equals 3. Okay. All right. So I hope that was helpful, and I look forward to seeing you in the next video.